Hello, guys. Can you guys hear me? Are we live? Yes, we are live. We are live. Okay, that's good. So, what are we gonna do today? Um, hello. Yeah. So today, so let's just open this. Yeah, so last time we were trying this OpenAI mode, right? This project. So today we're gonna do what's up, Smith? We're gonna do an all-nighter stream. There are few things which I have in mind. Yeah, there are a few things which I have in mind, which is basically we don't have to use. So this was the plan we built last time, right? API नहीं मिला bro, इसलिए अभी ये stream करूँगा all nighter. Let's go. पार्टी तो नहीं की all nighter, stream तो कर लेंगे. So the idea here is कि I'm going to use zero AI, not even tab complete, and we are going to try to fine tune this project and start it and get it to a place where we can, confidently say that we have built something. So for starters, I think firstly we'll have to understand how like RLHF or like RLVR, right? This thing, how this thing works, and I think we should firstly, let me just LSC, let me make a directory practice RLVR and just get into that and conda activate flash AI, and let's see if I have CUDA NVIDIA. Let's see NVIDIA SMI. Okay, let me first check. रात भर बैठने वाला रहेगा तो बता, बोर हुआ तो आजा. So let me get this. Okay, so firstly let me build a todo.md and let's test whether we have the right NVIDIA drivers, and first start a clock. Let's see, timer which keeps moving like stopwatch. Paste online stopwatch. start. Yeah, this is good. So this is the time we are streaming, right? Very good. So we have 2 stopwatches running. Annoying keyboard. Yeah, that's crazy annoying. Let's anyway, so yeah. Is the stream quality good, bro? How's the stream quality, bro? Yeah, so let's first test this. Test a simple PyTorch script to test whether everything is running properly. This is the to-do, right? And we will also have rules. One, no using Claude Code AI agents like Claude Code, Claude Code and Cursor and corrects or Cursor. This is the rule 1, and second rule is no using tab complete also. We don't want tab complete. No tab complete. And next rule, these 2 rules are very important. We're not going to use any tab completes today. And don't stop until we get to go. This is train RLVR based pipeline from scratch, only using online preferences and docs, right? These are the rules, nothing more. Yeah. What else? So yeah, so this is the first to do. Test a simple PyTorch script. Check out the TRL. Check out what libraries you are used. The latest techniques. Start. So these are the first steps we have to do. Let me get into practice RLVR. Let's create a file. Test PyTorch CUDA compatibility.py. Okay, let me go to Google. Any random PyTorch script. Okay, so this will be here, my code will be here. This is the PyTorch documentation, by the way. Here we can do like the stream, guys, if you are watching. So this is where we're gonna check the PyTorch script. So let me look at examples. User guide, get started. Tutorials. We want examples. This is a good example to run, right? Let me paste this. So what it is doing, this is UTF-8, dtype is torch.float, import torch, diverge. So let me just get device as CUDA. Let me switch off the suggestions for 30 minutes. So torch.device CUDA. So here x is torch dot linspace. Let me see what happens here. So let me do Python test. So we have created 2000. So this takes the torch package contains data structures for multiple dimensions, linspace. So start number, end number, and the step count. Steps, okay. So from minus torch.py minus 3.14 to 3.14, we have created 2000 numbers on our CUDA GPU. Dtype is dtype. Let me just see how to check if CUDA is installed by Torch. Torch, import torch. Torch.CUDA is available, right? So let me put this here. Python um 3.11. Okay, here we'll do import. Now we'll do torch.CUDA dot is true. Okay, we have CUDA. Let's see the device number. torch.CUDA dot device underscore count. It's 1. Okay. Let's see the current device. It should be 0 because the default one is 0 generally. So torch.CUDA dot current underscore device 0. Okay. and let's see the name of that device. So let's do, these are all Python commands in torch.coda dot device 0. Okay, this is the device, this is the code object number, and then let's see the name. So torch.coda dot get underscore device underscore name of the which device, the 01 device. So it's 5070 Ti which we have, right? And yeah, so here we are. So okay, let me just exit this. Now let me run the above. Okay, so this is okay. So why now is torch.signx. This will be sign of that, sign of those numbers from -pi to pi. Okay, so it will go from sine of pi by 2 is 1, sine, right, and then sine of pi is 0, sine of -pi is 0, sine of -pi by 2 is 1. So let me see, print y dot shape. This should also be 2000. So this is running. Why is it taking so much time? I dot shape. Yeah, 2000. So this is good. Now what are they doing? They are taking, let me not print this anymore. Let's remove this. They're taking random A, B, C, D, and they're defining a learning rate. That's fine. This is 10 power minus 6, 0.00001. 14 range to 1000. What are they doing? Let's see. So y predicted is a plus b times x plus c times x square plus d times x cube. So now it's one note. So let me sign in. Anymore, yeah. So this is just an equation, cubic equation. Loss is something which you predict minus the true values times power of 2, you sum them, dot item. Okay, 50% 100 is 99. You print. For every 99 numbers you're printing. Grad y 2 times this, okay. Grad b. Okay, they have manually counted the dot sum, update learning weights, printing this. Okay, let's see what happens. At least we are just testing the flow. So is this running? Okay, so it ran something. I think so. What we are trying to do is we are trying to fit a cubic equation. So equation visualizer. So here if I put, let's say, this equation, y equals to, let's say, 0, 0 is 0, and this is 0.8 times x, so 0.8 times x, and then what we're doing is 0.004 times x square, so plus 0.004 times x square x, and then I do power 2. How do I do square? A square x square. So x square, okay, 0.004 times x square plus it is minus 0.09 times x power. How do I do power here? 3. So if you look at this function, right? This function is, so we are trying to fit the sine of x, right? So sine of pi, so sine of 0, it should be 0, which is right. If you look at this, this is 1.7 and 0.9, right? So if I'm not wrong, 1.7 is 1.7 times 2 is 3.4, right? And pi is 3.14, right? Well, yeah. So it is almost trying to fit it. It's not quite there yet. But yeah, this is trying to fit the sine wave, which it did in the range it was trained into. It's minus pi, so this has to be minus 3.14. 2 plus pi is 3, so that's why I think it's still not there yet. But I think if I train more, this will be better. So if you look at the loss, is still 9, right? So let me train for more. Let me train for 6,000 steps, let's say. And let me see what happens. So the loss is going down. It's 8.8 now. And these values have improved, right? So the more the loss is smaller, this will look like an sine of x function, right? Let's do even more. Let's do 10,000, or let's say 20,000. So now that we're training it for 20,000 steps, so cubic equation, I think it's good enough just to fit basically only this much, loss of 8.8, I think. So it's very interesting, like what kind of equation should be there to so this is a non-linear equation. That's why we could fit like a sine function, right? But what if we train a neural network to fit this sine function? How good it would be? So that is like a different question. And I think plotting that is kind of tricky, and that a very interesting project. But at least we checked whether we have a torch device, and that was our first goal. So we are there. So we have done this one. So we have write NVIDIA drivers, tester simple Python script to test whether everything is running properly. Now we will go to RLVR. So switching to RLVR, okay. Let's go to RLVR. So this was the paper which launched everything. I think RLVR was started by DeepSeek R1. This was the first paper, right, which started all of this trend from DeepSeek, right, which crashed the markets and all those things, right? So these guys first introduced the GRPO. If you look at this training algo, right, yeah. So here it is. So they first introduced this GRPO, I think, and so they use like a smaller model. If you read this, it's a RL algorithm, right? So R10 is basically using zero supervised fine tuning, I think, and R1 is using a little bit. So this is the algo, and this is the advantage, I think. No, this is the advantage, and this is the function, the cost function, which they are trying to train on. So here you can see this is a clipped advantage, right? And then they are subtracting the KL divergence. And if you see this is how Kullback-Leibler KL divergence between the train policy and the reference policy is incorporated into the training process. So it's kind of interesting. Let's not go too deep into this. And what we're going to try to do is, let me search. So what libraries are used to do GRPO? So this is like an article. So TRL is the main library, right? So we have landed to a course implementing GRPO and TRL. So TRL is the main library which does all this, right? So let's read this thing out loud, and then we'll try to implement this. So the next thing is, what libraries are used to do GRPO? So we have Whirl, we have OpenRLHF, we have TRL. This is from Hugging Face. Then we have VLLM, we have Onslaught. So this is DeepSpeed is used often for managing memory and distributed heavy RL runs across multiple GPUs. So when we have multiple GPUs, right, we are generally doing this RL thing, right? Also, by the way, I'm still using this, what do you say, the wrong, so connection is kind of poor. We just solve that part. Yeah. Yeah. This is okay. Anyways, let's go to this. So let's focus on TRL today. Yeah. So start with check the code. Implement RLVR in TRL. And then, so this is the main thing now. So we have updated the to do, and now we're gonna try to code this here. So TRL run .py. Let's see. So in this page, we'll learn how to implement group GRPO using transform material library. We'll explore GRPO concepts, TRL's GRPO trainer using snippets from official TRL documentation to guide us. This chapter is aimed at TRL beginners. If you're already familiar with TRL, you might want to also check out the OpenAI implementation of GRPO. Okay. And first, let's remind ourselves of some concepts. Group formation. The model generates multiple completions for each prompt. So if you look at what GRPO does, right? How do I zoom out? View. So if you look at how GRPO works, we are sampling multiple trajectories, right? Last time I explained this. So we write it. So how does this work? So what we do is we sample multiple trajectories for a prompt. Then what we do is the LM for basically a prompt you want to train on. Then the LM gets rewarded for the right prompt, right answer. And the advantage is, so a group advantage is calculated based on how good our answer is compared to the other trajectories, right? And fourth is so you add like a add a reasoning token to give the model space to think. So if you have looked at, the reasoning part of things, right? The first Owen model used to reason, right? So this one is also good at reasoning. So this is how that feature is implemented. For example, let's say you do tell me who is better, Cristiano or Messi, right? This is our question, let's say. And you make the model, so the model will answer, right? I think Messi is better, right? But we don't want answer to look like this, right? So what we do is we do a supervised fine tuning on this. So what we tell the model is, you don't answer directly, you do some reasoning, right? Like this, and you add those reason tokens. In between, the model will think, right? This reasoning will happen, whatever, like Messi is more better at dribbling, he has won more, he has won like more trophies than Ronaldo, but Ronaldo has more goals, more penalties. Maybe that's why he is called Penaldo, but penalty taking is not good. So this can be like good metric. So this can be like the reasoning, and then you can say that Messi is better, right? So this is how you supervise fine tune it, and then what you do is you sample like multiple trajectories with different reasoning by changing the temperature of right? So once you change the temperature parameter, you can sample very different kind of reasoning based on the info the model has. And once you have that, you can actually give reward based on the conclusion itself, not the reasoning. So you give a reward based on the conclusion, and based on that reward, right? Based on this reward, you're gonna get the advantage and reinforce this part. So this is the basic idea of how GRPO works, like reasoning in LLMs. And if I want to test this out, I think they have a script. So yeah, so this is the group formation. So TRL does this for you, that it creates multiple completions. Then preference learning. The model learns from a reward function that compares groups of completions. So this is the group preference policy optimization. Training config. So the model uses configuration to control the training process, which is good. Then how what do we need to do implement GRPO? Define a data set of prompts, define a reward function that takes a list of completions, returns a list of rewards. Okay, so for all the completions, right, the reasoning traces, we need specific reward. So so prompt multiple reasoning trajectories with multiple conclusions, or it could be anything for that matter, and then you say reward for each trajectory. Configure the training process with GRPO config. Train the model using GRPO trainer. So this is the config. We have to understand how it is there, and then you have to train the model using GRPO trainer. Let me just open the TRL docs. And here, let me open GRPO. And okay, so here we have it. Okay. So they have examples also. This is good. So let me just try the minimal example first. Okay. So let me just open this on the side. Let me try to type everything out, because that will be like better for us to understand, right? I don't want to just get into pure white coding. So from TRL, and we don't want this also, no auto completes. Yeah. So from TRL, I want to import GRPO trainer and the GRPO config. But do we have TRL? So which interpreter we are on? So let me just open this thing, clear ls import TRL. We don't have TRL, right? Okay. So conda info. So we have an environment named PyTorch. We have an environment named Crocodile, right? So I think let's install. So how do we install? Pip install TRL. Let's go. That is nice. So let's again do Python for TRL. Okay, this works now. So we installed these libraries and TRL 1.7.1. That is good. TRL version. How do we check version? Pip TRL. how to check version of a installed Python. So you do pip dot version pip library pip show. Okay, pip show trl, pip show trl. So we got it. Version is 1.7.1. Summary, strain transform language module RL. Author is this guy. License is Apache 2. That's good. Hi guys, welcome to the stream. Do ask questions if you have any. Feel free to hop into the convo also, and do like the stream and share with your friends. So yeah, so we have TRL. Okay, and let me go back here. So data sets, we are importing some data set. Split is strain. Okay. Minimal example. But then what is this data set? Let me check sample DRL GRPO datasets. So this is a reasoning math data set, right? Can we download this? Let's see. So GSM 8K. So this is OpenAI. Okay. How big is this? Output check. This should be there, right? Files. Okay. Yeah. So this is 5.9 MB. This is from OpenAI. So let's download this data set. Go back, dataset card. Tina makes, okay, so these are like good reasoning kind of problems, right? हेलो भाई पूरी रात करने का प्लान है, आप रुक रहे हो तो रुक जाओ. So this is a math data set. We are trying to do coding, but let's start with math. How do I download this? So this is an MIT license, which is good. Dataset studio, files, card, okay. So how to download again face dataset. How to downloading datasets? Okay. Okay, just name it. That's good. So data equals to load dataset. Load dataset, and I just put the name, right? So what's the name of this dataset? GSM 8K. GSM 8K. This is the dataset, and let's see if I can do this. So print dataset dot shape. Pew, chicky chicky pew. Okay, so I think here .py. Maybe it will download that dataset, I think. Let's see. Oh, okay. That's sad, bro. So what's the error? Okay, so we have to put this also, I think. ID also. So let's put this, and Isa. Is this what we do? Let's see. Yeah, I think it's so okay. You're sending an authenticator request, value error. Config name is missing. Please pick one of the among the available configs, main and Socratic. Socratic, okay. So what is this? This is the main, and Socratic is what? What's the difference? Socratic is set .xct visit card leaderboard set viewer. Okay, let's see what it is. So each instance contains a string for the grade school level math question and a string for the corresponding answer with multiple steps of reasoning and calculator annotations. For the Socratic config, each instance contains a string for grade school level math questions, a string for the corresponding answer with multiple steps of reasoning, calculator annotations. So let's go with main. Now I don't know why we are downloading this data set, but we don't want reasoning data set as such, right? Why do we need data for GRPO though? Why are they saying we need data? Define a data set of prompts. Okay. Simple reward function. Okay. Then configure training. Output directory, number of training epochs per device trained, batch size is 4, gradient accumulation steps is 2, logging steps is 10. Okay. Here's the trainer. Model is my model. Args is training args, train data set, what function, trainer got trained. So your dataset should contain prompts that the model will respond to. The GIPO trainer will generate multiple completions for each prompt and use the reward function to compare them. So, okay. So reward function is crucial. It determines how the model learns. Here are two practical examples. Okay, let's understand these examples. So without understanding examples, we shouldn't proceed, right? We know the general flow, and also we'll have to decide on a task, right, to check out the training for. So here is one of the example. Based on completion length. So here what they're doing is completions, we're taking some arguments, we are returning float of length of completion for completion and completions. Based on matching a pattern. So this reward is, okay. So you get 1 if we match this pattern, regex pattern, else it is 0 for C in completions. Okay. So what this is doing is basically if we are getting these think tokens, anything in between, and then answer tokens. So this is a good reward, I think. So we are giving more reward for longer completion. Okay. Okay. And so we are to config. Let's see the parameters. So output directory is fine. Number of completions for each prompt, per device trained, batch size 4. Okay. Login steps, speed of generation. Okay. The number of generations parameter is particularly important as it defines the group size, how many different completions the model will generate for each prompt. Okay. May not provide enough diversity for meaningful comparisons. 4 to 16 provides good balance between diversity and efficiency. Larger values may improve learning but significantly increase completion costs. That's fine. Memory management. So, hi guys, welcome to the stream. You guys can drop in a question if you have, and do comment. So, tips for success. This all is fine. I just want to know how the reward function design is working. Okay. Several effective approaches to reward function design that you can adopt for your own GRPO. Length-based rewards. Okay. That are too short or too long. Okay. Length-based rewards. Oh, this is nice. So if ideal length is 10, short length reward 1. Okay. Yeah. This is token length, I think. Well, this is fine. Rule-based reward for verifiable tasks. Objectively correct answers like mathematics or coding, you can implement rule-based reward functions. Okay. One sec, guys. Okay. But I'm not understanding. Let us choose a task. So for tasks with objectively correct answers like maths or coding, you can implement rule-based reward functions. Okay. List of completions to list of answers to the problems on the list. And you need proper parsing. Answer is extract final answer. Okay. Reward 1 if answer is equal to correct answer, else 0. So this is like they're matching the final conclusion answer, right? If that is matching, you're getting 1. If not, it's 0. Except reward what happened is 0. Okay. So this is exact match. Math problem. What is 5 plus 7? 12. You get model answer 12. Difference 0, 1. 12 6 are 72. Model answer is 92. Difference is 20. Reward is 40.44. Okay. 5 minus 0, difference is 5. Okay. 0.5. Square root of 81,991. So this is some kind of weird kind of reward. It's using like an approximate closeness to the real value. Okay. You can also reward proper formatting, which was important in deep C1 training. So this formatting length of answer content is 0. Reward or append 1. Okay. So if it's thinking more than 20 tokens, and if the model is concluding with more than 0 tokens, we are already giving a 1 reward. Okay. And content in both sections. If match. Pattern completion. Okay. Then if this matches, so this part and this part I think is stripped, right? This one we'll have to check how this works. And partial reward for correct format with limited content. If this is the case, okay. So at least if this is the structure it is following, then we are giving 0.5 at least. If this is the sizes also, then 1 reward. And else we are giving 0. So this is good, right? So this is something which we can use. You'll follow an exercise to implement grep and TRL, okay? So let me open this in new tab. I think this one is useful. I'll take a break of 5 minutes, get me some milk, and I'll just go to washroom and come back. So till that time, you guys can enjoy some copyright free use music. I'll be back. I'm back. So let's see. Yeah. Hello, fellow viewers. Do like the stream, do chat if you wish to. And so what we're gonna do today is we are doing reasoning, right? We're training our LLMs to reason. Yeah. So so let's go to like proper this. TRL this. It's data sets, transformers, TRL, accelerate, bits and bytes, progress bar. Okay, so here, yeah, so let's just import all this. Peft LoRa config. So you're basically why do we want Peft? Let's see. So Peft is for lower rank fine tuning, Q LoRa or LoRa. So yeah, I'm drinking some protein powder with A2 milk, guys. Let's go. There's a lot of sai also. So we don't have hybrid cache. I think we will have to install these versions. Let's install them. Let's install this. This is damn yummy. We want flash attention also. So install this. Okay, we have this now, and one sec, I want to do progress bar on. That's good. Yeah, so we have these things now. Let's again go to this and let's see if we can import these libraries. Your old cache, and oh, that's good. So our imports are working now. Important login weights and biases. Okay. Import 1 dB. Let's check this. So I'm logged in here. That's good. I want to load this data set. So in this case, we'll use small TLDR. Small TLDR. Let's see what this is. Subreddit. Okay. The datasets were designed for fine-tune of Reddit post. You can replace this training using Collab. But what is it doing? Okay, title, post, and the summary. Okay, that's simple. And let's see, dataset studio files. Okay, it's a very small dataset. That's good. So yeah, let's load this dataset for the prompts. And let's print. And we have this. Okay. So we downloaded this dataset, train dataset features, prompt completion, validation, and test. That's good. Now let's load the model. We'll use small 135 million parameter model. Okay. So let's say model ID is this one. So this is Hugging Face 135 million parameters, a very small model. So model equals to auto model for causal element dot from pretend and let me just do here like this. Model ID big F torch.deep type is torch. This should be auto. Okay, then device map is auto, attention implementation, flash attention 2. Okay. And it's good. And let's see, OPENAI, is it? That's good. So let's load LoRa, take advantage of LoRa to the number of trainable parameters and turn the mere equipment we need to fine tune the model. Okay, so we're gonna do LoRa training. Let me just train LoRa config, task type causal LM, R is 16. LoRa alpha is 32. R and LoRa alpha are basically two terms which tell how R is the rank and LoRa alpha is another parameter, how strong you want that. So alpha in, what is alpha in LoRa? Alpha param So constant, it's a scaling factor, how heavily the newly trained adapter weight influence the model base weights. And R is basically how smaller a rank you want. And target model is all linear. Models get perfect model. Get perfect model, okay. Model LoRa config, print model.print enable parameters. So let's do this. Let's run. So let me just move this here. So it's downloading the model now. Check. Yeah. So it's more downloading. It's very small model. Let's see. Some error. Okay, so we need flash attention to. Okay. Install. Okay, now it's happening. What is this error? Let's see. So let me solve this error. Pipe flash attention. The flash installs straight back to source before Windows and ground file. Expects a CUDA toolkit. PyTorch. Use WSL2. Okay. But I was doing this. How was it doing this? Okay, let me take help of AI to solve this installation error. I think that much we can do. So I am getting this flash attention to install error. What you doing, gang? So we are trying to understand basically reasoning in LLMs, how it happens, thinking basically. You remember the OpenAI O1 model and the DeepSeek R1, right? So we are trying to understand how they work, and we are trying to recreate it from scratch without using, vibe coding. We are checking the code and, everything what's happening in the backend. So if you have any questions in the process, do ask me. Here I'm using Cloud Code just because I'm not able to solve this flash attention to error, install error. So it's just a dependency. But if you want to see what we are doing, you can read here. So we are not using any Cloud Code Codex or cursor to train, no tab complete also, and we don't stop until we train something using RLVR. So we are doing really post training, what's happening in the field right now. So I am on Windows. Okay, what's this bull crap? Try this again. Google. Bam, 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 bam. Pop, 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 pop. Yeah, continue. Okay. The immediate error is the pip is trying to process from source. There's no official Windows wheels on PyP, and the build needs a CUDA toolkit, which isn't found. Hence, CUDA home variable is not set. Let me check what's on your machine. Check for enemies and CUDA toolkit. Okay. So it's saying torch versions, Clash AI imports this, torch princess.version, torch.version, torch.version.CUDA. Okay, it's checking the versions. Let me close this. If you guys have any questions, do ask in the chat. Pre-built Windows wheels. So it's checking for pre-built Windows wheels. Let me search this on my own. What do I get? Like included wheels unpublished anywhere else. CUDA 13. So it's saying just use HDPA, right? Let me check. So from pre-trained, and it's saying attention implementation is HDPA. Okay, HDPA. Okay, so Now let me see. Now is it working? Okay, so trainable params is 4 million. All params is 140 million, 3%. Okay, 8-bit GPU quantization is there. It's fine. Now what to do? Okay. This is done. This is done. This is done. Okay. Now that we have LoRa, GRPO can use the reward function to improve the model. In this case, we use a simple reward function that encourages the model to generate text that is 50 tokens long. So ideal length is 50. Let's define this reward function. Completions. So this is the format they wanted. Minus absolute of ideal length minus length of completion for completion and completions. So let's say ideal length is 50. My length is 20. This is 30, and I'm doing minus of 30. So anywhere if I go away from the ideal length, I'm getting negative reward. That is the logic. Define the trainable parameter, training parameters. So GRPO config, training arguments. You can check the training arguments class for more information. So training arms, what is this? So okay, so output directory should be GRPO. Okay, learning rate. S2 e.-5 per device training batch size is 8, gradient conversion. Okay, so these are like GPU related batch and okay. Then max prompt length is 5 and 2, so it will clip it, I think. Max completion length is 96, so it will stop after completing 96. GRPO config, okay. Number of generations is 8. Optimizer is Adam 8-bit, okay. Adam optimizer, number of training epochs is 1. Okay. Report to OnDB. Remove unused columns false. Logging steps is 1. Okay. Now we can initialize this trainer with model dataset and training arguments and start training. That's good. Let's just copy this. GRPO trainer, you're using some model. Reward function is our reward length, this one. Arguments is training args, train dataset, train. Okay, so we are using this dataset. Okay. Let's just do this. OnDB. So I'm just logging into weights and biases to check the trading curves. Okay. Okay. So GRPO project. Okay. Now let's just do this. TRL run.py. That's kind of easy, right? It's very easy. Okay. So let me just check with ChatGPT. Is CUDA or GPU being used? What is that bits and bytes error? Okay, so let's check the training. Let me refresh. Okay. Okay. GPU power usage. Okay. It's kind of nice, clean. GPU memory. System 21. Let me ask ChatGPT. So what all is login? So is it training? Yeah. Meow, check it, yeah. So memory used is this an MB? GP memory. How much is this? Wow, 100% of GPU memory is being allocated. Wow. Metrics for every logging step. As here, they are to use the training metrics. Expect metrics in these broad categories: loss, grad norm, learning rate, epoch. But I don't see any of it. Where is loss? Yeah, we don't have all that. Let me check. Yeah, no. this NVIDIA SMI also. So this is already using 15 GBs. My goodness, it's already bad. I'm streaming also. So let this happen. Okay, that's good. Let this work. Okay. Training takes around 1 hour on single GPU. Or by hanging face spaces. Push the model to the hub during training. If we set the push to hub argument to true and the model ID argument to valid model name, the model will be pushed to in. But it takes a lot of time. Huh? As you can see, the reward from the reward function moves closer to 0 as the model learns. This is a good sign that the model is learning to generate text from correct length. Reward from your reward function, the loss in the range of the metrics. Yeah, but I don't see anything. Where is the loss? One sec. I don't see. Okay, so because we are using 8 prompts, generations per prompt is 8, 64 completion generated per device per step. Max completion is 96 tokens. Only after the work plus reward calculation, backward path operation does the trainer reach a logging event. Yeah, so this will take time, I think. Should we put like a smaller config? Maybe. Or let this work out. Let's read the article till then. Define the training arguments. Okay. Interpret training results. GIP trainer logs the rewards from the reward function, the loss in the range of the other metrics. We'll focus on the rewards from the reward function and the loss. As you can see, the reward from the reward function moves closer to the zero the model learns. This is a good sign that the model is learning to generate text of the correct length. You might notice the loss starts at 0 and increases during training, which may seem counterintuitive. This is behaviors expected that the formation of the loss in GIP is proportional to the KL divergence. The training process and model has to generate text. So this is loss. Loss is increasing. Which steps? expected in GRP is directly related to magnitude formation of the loss in GRP is proportional to the KL divergence. So we are diverging from the original policy. Okay. But then how are we defining that loss? And then what is happening to the reward? The generation length is going close to 50. Before it was higher, so it is learning the pattern to generate like lower these things. Okay. Interesting. So is a 10 GPU faster or 50 70 Ti? Okay, memory bandwidth is faster. Checklist. Oh, we got into out of memory. So we got into this error. We are already out of memory. CUDA out of memory, not the bits and bytes warning. And it shows that GRP of open GRP ran out of memory. Okay. This is aggressive, right? So per device training guided animation is 8, 2 and 8. Training batch size, let's do 4. Or maybe 2 only. Let's say 2. Here I'll put 8. And then max prompt length to 56. This is 64. Number of generations 2. Maybe okay, 2 is fine. Maybe I'll do it. Maybe I'll do 4. 4 8-bit into logging steps 1 force trainer GRPO SDPA gradient checkpointing on. Atom torch and gradient checkpointing. Okay. Okay, I think we can run again. Let me check W and B. Okay, so we restarted the training now. Log completions. Log completions. Okay. Log underscore completions. So what is this log completions thing? Remove this line. Okay. Okay, new run started. Let's open this. Runs. Let me reload this. Why is this filing, bro? Hell no. Projects. Workspace. Yeah. Again failed? Let me stop this. Why is this again problematic? Okay. Since you already rushed the GI program, that cause the boom first and generating checkpointing off. Checkpointing off. Okay. Oh, let's go. We're training. Let me look at the logs. Nice. So, how many guys are watching this? No one is watching. It's good. How many epochs? Okay, so let's see the loss. Okay, this is the train. So reward is going from -195 to -187. So it's decreasing, which is good because we are penalizing the wrong length, right? And loss is kind of increasing, which is what we want, right? Because it has to diverge from the original model, something like that, right? KL divergence is increasing. We are trying to stop it. This is a part which I have to exactly dig into. I'll do it. Let it complete. It's taking a lot of time. Let me play some music till then. Copyright free. We'll use sounds.
All content created.
लोगों को तुम्हें यूज कर पाएंगे। बैकग्राउंड म्यूजिक
पैसा आ जाओ लोग के हाथ में।
Backup dancer or music to post online. Being familiar with your equipment is a little bit, and if you're not using a mic, then this wouldn't apply to you. But if you're using a mic, then great. And we're going to make sure that
I'm back.
बात दिल की राज रोने की सच कह रहा तेरी कसम तेरे बिन न लेंगे एक भी दम तुझे कितना चाहने लगे हम तेरे साथ जाएंगे तो तुम तुझे कितना चाहने लगे हम तुझे कितना चाहने लगे सारी दुनिया से तेरे इश्क तेरा मेरा ही तो है कह दिया है ये मैंने मेरे रब से भी इस रास्ते तू ना मिले उस पे ना हो मेरे कदम तेरे बिन न लेंगे एक भी दम तुझे कितना चाहने लगे हम तेरे साथ हो जाएंगे कसम तुझे कितना चाहने लगे हम तुझे कितना चाहने लगे हम जिथे जावे तू उथे जावे दिल जिसकी मैं जो तू मुझसे छड़िए तेरे टूट छड़िए तेरे संग संग रहा सर कट छड़िए मैं तो तेरे नाम रहना मन तेरे मेरे कहना मेरी आँखियों से हो लगा दी दूर ना तेरे
तेरे तेरी सनसनी रहती मैं रंग जाऊं तेरे रंग तेरी नींद से ख्वाब में अपना जोड़ूं तुम साथ न हो तो चार कदम न चल पाऊं तेरी राह पे राह में अपनी हो जग भूल जाए मुझे तुम नहीं भूलना तेरे संगे जीना मेरा तेरे संगे ढलना सच्ची चाहत का होता कोई मोलना तेरे मेरे नैना मेरा ढूंढना कि तेरे मेरे नैना मेरा ढूंढना सब छोड़ जाए तो मैनू छोड़ना कि तेरे मेरे नैना मेरा ढूंढना
Okay, so is it done? Oh, 39%. So let's just read it out what's gonna happen. I think we have done it quite nicely today. Just check this out. So what they're saying is, now that we have a reward function of length, let's say, and we have a loss which is increasing, let's also give it some other rewards, right, for a next run. So they had given them, right? Yeah, so this one is reasoning based, right? This coding reward function, test code solution, 1 if works, else -1. Okay, this is also nice. So okay, it's kind of very interesting. So this is GRPO trainer overview. Okay. Let me search. So all types of coding related rewards for GRPO. Execution based, format structure based, reference model based. Okay. Posterior reward. Rewarding reasoning processes in code generation. This is a good paper to read, right? So finally, what we're gonna do is, now that we have understood how GRPO is working, this was our plan, right? Yeah. So let me just get this away. So So what we're going to do here is build a minimal local product trajectory here. PO phase 1. What were we using? Fable 5. तू ही मेरी मंजिल तेरे बिना गुजारा है दिल मुश्किल तू मेरा खुदा तू दुआ में शामिल तेरे बिना गुजारा दिल है मुश्किल मुझे आजमाती है तेरी कमी मेरी हर कमी फिर है तू लाज़मी जुनून है मेरा बनू मैं तेरे काबिल तेरे बिना गुजारा है दिल है मुश्किल टू 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 So let's just understand GPU space requirements for GRPU on different sized models. Okay. the scaling laws. This paper is code generation, right? We are now at 51%. Okay. What was the basic idea? So basically, GRP using trace, which is reinforced based on alpha. This should as well the group environment only acts after the reasoning has completed and action has been sampled. So for long range tasks or loops of such actions, the complete trajectory of, let's say, a research agent could be trained using a reward given to the final model itself rather than individual environments. The LLM would train a model, have a conclusion, which involves many set of reasoning and action pairs, and then we sample multiple types of action reasoning items by the LLM to solve tasks for each. And then have a GI model even more to where we want it to be. Also, one caveat, the reward output could either be a GI or more inside the fiction of the output. So the main idea of this project was to hear this part, right? So this was basically the loopy, run loops and give reward to loop ending and conclusion. And this was basically the reward function is also like learned, and then that is used in place of a model real reward function. This is like a self critique. But this is basically present as while advantage actually. So this is not something new. So let's say I want to train a coding model of 3B with GRPO on long context coding tasks. Can I do it on this page right here? Okay, so tell what Yeah, so like what I'm reading currently is on larger tasks, right? How is the GPU planning done? So if you look at this part, so for 3 billion model and GRPO, even for like 2 to 4K context, you need 16 to 24 GB of RAM, VRAM. 48 GB is kind of comfortable, and the scales to like 32K context, you need 80 GB, and multi-GPU architecture increasingly useful, right? So parallel, right? So one is doing like inference, the 8 inference, right? And one is doing the training of the architecture. If you look at this, more generations, I would keep the 5070 Ti for development, debugging and run for your GB or a 80GB linear GPU server for actual 3B long context GPU and spying edge class server before you have the reward pipeline. The test execution architecture is nearly as important as the GPU choice. Server security matters. Should not be executed directly on the host running machine. Use that's cool. Okay, this is cool. So for RTX 6000 ADA, what's the rental price? So it's almost $1.80 per hour. So if I'm using for it for like 10 hours, I'm using 800. Could cost $7, right? It's fine, right? So like this is logical. Okay, that's fine. Where's the training? 62%. Okay, so I think we have done the training part of things, right? We understood how the sampling is working, how the code works, right? What all these parameters mean. This is like accumulation. So what it does is it infers something, the gradients, and accumulates to stick like for a bigger batch, right? It does multiple runs, it accumulates, and then it does the backward passing multiple runs. So, but yeah, at least we understood how this syntax works. Let's say I want to add another reward function. You just keep naming them, and you add it in this part, right? I think because this takes a list. So yeah. This is interesting. And how do you do the reasoning part, right? Reason, start, reason, and this part. I think we have to do a SFT on it. And once you do an SFT, you can. So we had that GSM 8K dataset, right? Which has the reasoning also attached with the conclusion. So what we have to do is we have to first do a reasoning, supervised fine tuning on it. And then what we can do is here, if you saw, where was it? Where was that complicated reward? Yeah. So here you saw this. Yeah, this reward. So this is kind of interesting. What you can do is once you train it to reason, you can increase this to, let's say, 200. Now the agent is forced to think for 200 tokens before it can conclude, and that somehow helps the agent to get to the final conclusion, because it somehow spits some kind of blabber in between those reasoning tokens, which is very much useful, right? So that's the reasoning part of things. So next time we'll add these rewards and also look at how the output works out. What I'll do is I will put those rewards, I'll do a training run, I'll save the checkpoints, and then we can start discussing on what was trained and how, and do real inference with that model. So you guys stay tuned for the next episode of the same. I'll let this run, and then I'll add this reward specifically, the reasoning one, and maybe also do a small fine tuning of what reasoning should do in the next stream, right? So stay tuned for that one. I think I'll sign off for now. And thank you for watching. Bye bye.